So as we begin our new lesson, let's think about the common ion effect. When we have two solutions, each with an ion that's in common, we'll look at that as the common ion effect. And one of the first examples reads, when we have a salt with an ion of a weak acid, it reverses the dissociation of the acid, and it literally does so by lowering the percent dissociation. Now let's make sense of what the sentence is saying. Let's say that I have a weak acid. We're going to call it HA. And the very definition of it being weak, it's giving us an equilibrium where we have H plus and A minus. Now, according to Le Chatelier's principle, if I have another salt, if we're looking at a salt with the same last name as this acid, so let's say that this was acetic acid, and so over here, let's say my salt was sodium acetate, so I have the same last name, then we would be applying a stress, adding an ion that's in common with this same last name. So let's say I had sodium acetate, and we'll just call that Na. So I have my Na plus and A minus when it dissociates. So I have extra, I'm adding stress, so I'm increasing my A minus. So that means Le Chatelier's principle is going to push my equilibrium to the left, which is going to use up or draw out my H plus ions, making this less acidic, which is going to increase the pH of the solution. So the same principle applies to salts with the cation of a weak base. So let's use some general chemistry here. Let's say that I have a base put into water, and we have BH plus formed and OH minus formed. So it's telling us if we put in a salt who has the same first name as the base, say ammonium chloride, or let's see, thinking of something that's in common. Well, the stress says that if we are increasing our BH plus, then we are shifting our equilibrium left. Again, so we are removing, we're using up that OH, which is making it less basic, so more acidic, so it's lowering the pH of that solution. So the common ion effect says, so we're going to be studying an acid-base equilibrium. So we're studying some sort of equilibrium, and then really according to Le Chatelier, we cause a stress, and the stress is putting something in common with it and watching it shift from left to right or right to left, but then calculating this based on an ice chart. So as we consider the approach when we are solving these problems, we need to identify the major species in solution, consider their acidity or basicity, identify that equilibrium, and then really look at that equilibrium aspect of the ice chart. So let's look at an example here. Question number 1 says, what's the pH of a solution made by adding 0.3 moles of acetic acid and 0.3 moles of sodium acetate in enough water to make a 1 liter solution? And we're given the Ka of 1.8 times 10 to the negative 5. Well, let's look at the chemistry here. We're told that we have acetic acid, which is a weak acid. And the very definition of a weak acid says that it sets up an equilibrium. And it will do so by creating ions of hydrogen and acetate. So let's write this out here. We have HC2 and our Ka given is 1.8 times 10 to the negative 5. We're also given that we have a salt. We have sodium acetate. So we have Na C2H3O2. And a very definition of a salt says that there is not an equilibrium. It's a strong electrolyte. So it's going to dissociate into Na plus ions and acetate ions, and it's going to 100%. So we're told, since it's 0.3 moles in 1 liter, so we have 0.3 molar sodium acetate. That means when it 100% dissociates, we're given 0.3 molar of sodium ions and 0.3 molar acetate ions. Now what we care about here is our acetate, because that is what is in common with our weak acid that's in equilibrium. So if I look over and set up my ice chart for my weak acid, I also can see that my initial concentration, I have 0.3 mole of acetic acid, and I know that I have 0 and 0 plus, since here's my common ion effect. Over here I started with 0.3 molar of that common ion, the acetate. So down here, my change, we know as time goes by, we lose acid and we gain product. So this would be 0.3 minus X. This would be X. And technically this would be 0.3 plus X. So here's where the math gets a little easier though. We're going to assume that 5% rule, and we're going to toss out the plus X and the minus X. So in other words, when we are looking at the amount of acetate ion that's being contributed to this equilibrium from the weak acid, compared to the amount of acetate ion coming from the salt, it's negligible. It's not worth adding into the math. The Ka simply becomes products over reactants, and look what happens. So we have our Ka is equal to our products, so X times 0.3 molar over my acid of 0.3 molar, and the math simply shows these canceling out, and X becomes the Ka of our weak acid. Remember, we let X stand for hydrogen ion, and the negative log of that value, we get our pH. So we can see here that our negative, or 0.3 and our 0.3 cancel out. So X is equal to 1.8 times 10 to the negative 5. So let's plug in our negative log of 1.8 times 10 to the negative 5. And we should get 4.74 for our pH value, which would make sense knowing that it's a weak acid. So let's go back and look at what we did. The pH of a solution, if we have 0.3 moles of acetic acid and 0.3 moles of sodium acetate. So we know that our acetic acid is a weak acid. We set up our equilibrium because we know that a weak acid forms an equilibrium, and we're given the equilibrium constant. Sodium acetate, however, is a salt, and by definition, 100% dissociates. So we know that if I have 0.3 molar of my sodium acetate, I have 0.3 molar of acetate. And acetate is a common ion with my acetic acid conjugate base. So by Le Chatelier's principle, if I have a stress, so I have extra ions here, we're going to shift this equilibrium left. All right, so I'm going to set up my equilibrium constant. So what I added here, instead of having 0 and 0, like I normally would, if I did not have that other piece, we would have 0.3, 0, and 0. And then we would have minus X and plus X. Remember when we would set up this equilibrium, we would have X times X, right? But I added that 0.3 molarity extra acetate. That was a stress on this. So we have 0.3 M times X all over 0.3. And that makes our math was easy in this case. It's not always the case like that. So we have those cancel out. We have x was 1.8 times 10 to the negative fifth. Our x represents our hydrogen ion concentration. And we know that if we do the negative log of x, let's look at another example here. We want to calculate the pH of a solution containing 0.085 mole nitrous acid, and we're given the Ka value, and 0.1 molar potassium nitrate. So let's write out, we know our nitrous acid is a weak acid, so we have HNO2. And again, definition of the weak acid is that it forms an equilibrium. H plus and NO2 minus. And we have our Ka of 4.5 times 10 to the negative fourth. We're also told that we have potassium nitrite, KNO2. And again, this is not forming an equilibrium because potassium nitrate is a salt. It will 100% dissociate into K plus ions and NO2 minus ions. So we were told that we have 0.1 molar concentration of potassium nitrate, which means we have 0.1 molar of K ions and 0.1 molar of nitrite NO2 minus ions. So we can see our common ion that we have here is our NO2 minus. So we have a greater concentration of that. Again, Le Chatelier say that if I increase here, we're shifting left. So let's write down our HNO2, we're told is 0.085, right? So we're going to lose. So we're going, and we have 0 initial, and then we did have 0, except for we don't have 0 NO2 minus. We have 0.1 molar of it to start with. And so again, we're going to minus x. We're going to plus x plus x. So we would have 0.085 minus x. And then for our hydronium, we have x, and then 0.1 plus x. And again, we're going to assume the 5% rule, and that x is so negligible that we can take that minus x and the plus x and just cross them off. So then we're left with our Ka, our 4.5 times 10 to the negative fourth is equal to our products over reactants. So 0.1 times x over 0.085. So if we simplify here, I'm going to do 4.5 times 10 to the negative fourth times 0.085, and then divide by 0.1, and I get x is equal to 3.825 times 10 to the negative fourth. Now remember, our x is our H plus concentration here, right? X and x. So I can do the negative log of 3.825 times 10 to the negative fourth to get a pH. Negative log of 3.825 times 10 to the negative fourth to get a pH of 3.42. So very similar to the ice tables we did in the previous unit. The only difference is that we are adding this common ion. So we are initially starting with more of a product on the right, so therefore it's shifting our equilibrium left and affecting the pH. Let's look at another example here. Here we want to calculate the fluoride ion concentration and pH of a solution. So we've got HF and we have HCl. Okay, so let's write HF is not a strong acid. So it sets up an equilibrium, gives us H plus ions and F minus ions. Then we have HCl. And HCl is a strong acid, does not set up equilibrium. It 100% dissociates into our H plus and Cl minus ions. So we were told that we had 0.1 molar of it. So 0.1, 0.1, 0.1. And notice here that our common ion in both of these is our H plus. So let's look over here, our HF, since it's our weak acid, we do need to look up our Ka value for that. So I'm going to get out my Appendix D and look up Ka, and we see that it's 6.8 times 10 to the negative fourth. All right, so we're told that our HF, that we have 0.2 molar HF. And again, we know that we started out with so initially 0 plus 0.1 molar, since this is my common ion, 0 plus 0.1, and again, 0 of my product. And then we're going to minus x, plus x, plus x. So at equilibrium, we would have 0.2 minus x, 0.1 plus x, and x. So again, we're going to just start assuming from here on out that these little minus x's and plus x's are nulled and voided. So we could actually even simplify our ice table from here on out. We can just go, okay, what we're starting with is what we're given. We know that it's going to be the concentration of the common ion, and then instead of 0, since we're adding x, and then the other ion is x. All right, so now we can set up our Ka expression here. So Ka is 6.8 times 10 to the negative fourth, which is equal to our product, so our 0.1 times x over 0.2. And let's solve for x. So 6.8 times 10 to the negative fourth times 0.2. And we're going to divide that by 0.1. So x is equal to our F minus, our concentration of our F minus, actually. So that's going to give us our fluoride ion concentration, which is 0.00136 m. Now, to find our pH, remember pH is the negative log of our hydronium ion concentration. And we know our hydronium ion concentration. This common ion right here are 0.1. So the negative log of 0.1, I have to plug that in here, negative log of 0.1. Oh, we get a pH of 1. pH of 1.00. Remember, we go to 2 decimal places. So in this case, our common ion was actually the H plus, giving our fluoride the X. We didn't know. So we were able to pull out our fluoride ion concentration and then go back and calculate our pH, knowing the hydronium ion concentration.